So let's do the extra practice homework. So 2 to the 3 minus x equals 7. So if all of your x terms are isolated in the exponent of an exponential term, then you can just take the log of both sides to undo it. So I'll take log base 2 of the left and log base 2 of the right. Log base 2 of 2 to the thing is just thing. So now we've got log base 2 of 7, which is just a number. So if I add x to both sides and subtract this from both sides, I'll get 3 minus log base 2 of 7, which is the answer. Okay, next one. So 9 to the 2x plus 1 over 3 equals 27 to the 4x. So there's a couple things we could do. We could multiply by 3 on both sides. I think what I'm going to do is I'm noticing all of these bases are powers of 3. So I'm going to rewrite this as 3 squared is 9. And then this is 3 to the first power. And then 27 is 3 cubed because it's 9 times 3. And so now I can multiply the exponents here. So this gives me 4x plus 2, and then if I divide by 3 to the first power, that's like subtracting 1. So I've done that, and then here I've got 3 to the 12x. So now you can think about this as taking log base 3 on both sides, or you can think about if the bases are the same and the values are the same, then that means the exponents must also be the same. So that means 4x plus 1 must equal 12x. So I'll subtract 4x from both sides, giving me 8x equals 1, or x is 1/8. Okay, let's do 2. So 5 to the x over 5 to the opposite x equals 3. So you could multiply by 5 to the opposite x on both sides, or I think what I'm going to do is I'm going to think about it this way. 5 to the x minus opposite x. So that's 5 to the x plus x equals 3. Or 5 to the 2x is 3. If I take log base 5 on both sides, that gives me 2x is log base 5 of 3, or x is log base 5 of 3 over 2. Okay, 3. So ln is pronounced natural log, as you remember, and it's log base e. So log base e of 2x plus 1 is 5. So this is very similar to the first one where we just had an exponential and we took a logarithm to undo it. Here we have a log, and we can use an exponential to undo it. So if I have e to the power of log base e, those will undo each other. And if I'm doing it on the left, I also have to do it on the right. So e to the natural log of this stuff equals e to the 5th. So that means 2x plus 1 is e to the 5th, which means x is e to the 5th minus 1 all over 2. All right, let's do 4. Do I have enough room for 4? Probably. So 4 says log base 3 of x plus 1 plus log base 3 of x minus 1 equals 0. So this is one of those recognize the situation when you can use a logarithmic simplification identity. So if I have log plus log, that's the same thing as log of like the two insides multiplied. So here I've got x plus 1 times x minus 1, and that's equal to 0. So x plus 1 times x minus 1 is just going to be x squared minus 1. And then, I guess let's rewrite the log. And then if I exponentiate each side as a power of 3, I'll have 3 to the log base 3 of this equals 3 to the 0. 3 to the 0 is just 1. So that means x squared minus 1 equals 1, which means x squared is 2, which means x is plus or minus root 2. Whenever you have a problem like this, it's worth checking, do both of these answers actually work for the domain of the functions in your original setup? And they don't, so if x is negative root 2, then I'd have log base 3 of negative root 2 minus 1. And remember, the log of a negative number isn't defined. You could think about it graphically, like here's what log looks like, and pretty clearly, negative values aren't in the domain. You can also think about it conceptually. 3 to what power gives you a negative number? And the answer is there is no power of 3 that will yield a negative number. So it's not actually plus or minus root 2. It's actually really just plus root 2. Okay, let's keep going. Okay, so 5 says something to the 12th power. So let's see, fourth root of x cubed over cube root of x to the 4th all to the 12. Okay, so let's rewrite these roots as exponential expressions. So 4th root is like raising something to the power of 1/4. So this is like x cubed to the 1/4. This would be like x to the 4th to the 1/3, and that's all equal. That's all being raised to the 12th. So then I can rewrite this as x to the 3/4 over x to the 4/3. And so then I can rewrite that as x to the 3/4 minus 4/3. Or maybe it'll be better to, all right, so I was going to do this. Here, to figure out what this is, we would have to put these under a common denominator. So I could multiply by 4 over 4 and 3 over 3. So that way I'd have 9/12 minus 16/12. So I could do it that way. But actually, let's try and do it this other way first. I'm actually going to multiply, right? I'm going to exponentiate the numerator and the denominator separately and see what that gives us. So x to the, let's see, 3 over 4, or I guess let's do it this way. So 3 over 4 times 12, and this is 4 over 3 times 12. And that I don't know, maybe it's all the same to you, but this feels a little bit nicer to me. So 12 divided by 4 is 3, so this is x to the 9th. 12 divided by 3 is 4, so now this is x to the 16th. And then 9 minus 16 is negative 5. So this is 1 over x to the 5th. Oh, except it's not, because it's actually it's actually 1 over x to the 7th. Cool. Problem 6 says x to the 1.5 over x squared times root x to the power of negative 3. Okay, so I want to simplify the insides here. So x to the 1.5 divided by, this is the same thing as x to the 1/2. So I have x squared times x to the 1/2. So that's the same thing as x to the 2.5. Oops. Because I added the 2 and the 1/2. So now I've got 1.5 minus 2.5. So x to the 1.5 minus 2.5. So that's the same thing as x to the negative 1. And that's being raised to the negative 3, so that's the same thing as x cubed. Yay. Okay, 7, 5th root of x to the negative 3 times x to the 28 all over x squared. All right, so let's see, 28 minus 3 is 25. So here I've got 5th root of x to the 25th. So then this is x to the 25th time, or like we can rewrite this as to the 1/5 power, which is the same as now multiplying the exponent by 1/5. So 25 over 5 is 5. And so now this is x cubed again. Cool. So it occurs to me maybe that went a little bit fast. So I applied a couple of different rules here. So this is the one where it's like a to the b times a to the c equals a to the b plus c. So that's why I added together 28 and negative 3 to become 25. And then here is the one where if I have a to the b to the c, that's a to the b times c. So here and before I did that, sorry, I rewrote fifth root as to the 1/5 power. So that was kth root of x is x to the 1 over k. So I rewrote the root as an exponential. Then, if I have an exponential being raised to a power, I multiply the two exponents. So I got the 25 times the 1/5 has given me to the 5th. All right, great. So let's do which one? All right, so we've got the cube root of the 8th root of x cubed times x times the square root of x times the 4th root of x. Okay, so let's like start on the insides and start simplifying our way out. So this is the same thing as x times x to the 1/4. X is the same thing as x to the 1st, so that's now going to be x to the 1 1/4, which is the same thing as 5/4. So I've got, and again, all the rest of this is still here. I'm just simplifying the part that was inside there. So x to the 5/4, the square root of that. I guess let's rewrite this part now. So this is the same thing as x cubed to the power of 1/8. And so that's going to be x to the 3/8, and then that's like cube root of everything still. So instead of square root, let's raise that to the power of 1/2. So here I've got x to the 3/8 times x to the 5/4. Let's rewrite this as to the power of 1/2. So 5/4 times 1/2 gives me 5/8. Oh, this is working out very nicely. So 3/8 plus 5/8 is going to give me 8/8, which is just x. And so really all of this is just the same as cube root x. Okay. And that's the end of those ones. Great. Let's do more medium. Okay, more medium is apparently starting with number 3 because Word's auto numbering is always trying to battle me. And I think it always wins. It always wins. I'm okay. All right. Cool. So what can we do here? Let's, I want to undo this denominator. So let's multiply both sides by this thing. So I'll have 2 equals e to the negative x times 3 minus e to the x. And let's distribute in the e to the negative x. So now I have 3 e to the negative x minus e to the negative x times e to the x. And then this warrants a little bit of thought. What is this thing? Remember, e to the opposite x is the same thing as 1 over e to the x. So this is just saying e to the x times 1 over e to the x. So that just gives us 1. Cool. Whoops. So 3 e to the opposite x, and then that's 1. So let's add that 1 over here. So now I've got 3 is 3 times e to the opposite x. We'll divide by 3 on both sides. So now, well, I guess we could do this. It's a little bit silly to think of it this way, but I guess we could do it this way. So this is the same thing as 1 over e to the x is 1, so now I can multiply both sides by e to the x. We could also, at this point, think about taking log base e of both sides, take natural log of both sides. And that would also make sense. Let's do this. So, what power of e equals 1? Must be 0. Cool. What if we'd solved it the other way? What if we'd taken natural log of both sides? I'd have natural log of 1 on the left. Natural log of e to the opposite x gives me opposite x. The log base anything of 1 is just 0, so that means opposite x equals 0, which that means x is opposite 0, which is also just 0. Okay, so we got the same thing if we solved it the other way. Let's do number 2. Oh dear. Okay, number 2, which comes sequentially after 3 in the problem set apparently, is log base cube root x of 16 is 12. We're solving for x. Okay, so let's just apply the definition of logarithms, or let's rewrite this as an exponential. So the base to the power of 12 should be 16. So cube root x to the power of 12 should be 16. Cube root is the same thing as x to the 1/3. So now we can multiply those. So 12 divided by 3 is 4. 16, so that means x equals plus or minus 2. And then let's just double check, would it make sense for x to be negative 2? Well, it does. If it definitely makes sense for x to be positive 2, because then we have a positive base there. It also makes sense for it to be a negative base, because you could certainly have, it's not going to be negative 2, but you could imagine like log base negative 2 of something equals something, and that's just saying negative 2 to some power equals something, and that's a perfectly sensible statement, so that's okay. So I think either of those could work. All right, let's think about problem 3. So here we've got natural log 3 plus 2 times natural log x plus 2 equals 5. So a couple things we could do here. We could try and natural log 3 is just a constant, so we could move it here. I'm gonna solve it two ways. We'll move this over to the other side, divide by 2, and then undo the log. So here I've got natural log x plus 2 equals 5 minus natural log 3 divided by 2. So again, I subtracted that divided by 2. So now I can exponentiate. So I'll have e to the natural log equals e to the that stuff. So that gives us x plus 2 equals e to the that stuff. And then I'll subtract 2, and that's correct, but it's not particularly nice. Let's see what happens if we do it the other way. Done the other way, I'm going to apply like the log simplification rules. So I know because I'm multiplying my log here by 2, I can rewrite this as like x plus 2 squared, because I brought the 2 as the coefficient up as an exponent on the inside. And then if I'm adding, that's the same thing as multiplying on the inside. So, whoops, so that's x plus 2 squared equals 5. Okay, so now we can undo the natural log by exponentiating. So here I've got 3 times x plus 2 squared equals e to the 5th. Now I can divide by 3 on both sides. I'll take the square root of both sides. I guess let's just do that. E to the 5th over 3, and then I'll subtract 2. So x is negative 2 plus or minus root e to the 5th over 3. And that might not feel a lot better to you. It looks better to me. Let's actually rewrite this thing where I've just been writing frowny face. So negative 2 plus e to the 5 minus natural log 3 over 2. So if you ever have e raised to an expression that involves natural log, that should be sort of like a key, like a clue to you that you could simplify this further. So I'm going to turn this into that by using exponential simplification rules. So let's see, this is the same thing as e to the 5 minus, no, what am I trying to do here? Yeah, natural log 3 times 1/2, which is the same thing as raised to the 1/2 power, because then I'd be multiplying the 1/2 in like that. And this is the same thing as square root. Okay, so now I've got negative 2 plus the square root of this whole thing. And if I have 5 minus natural log 3, that's like saying e to the 5th divided by e to the natural log 3. And e to the natural log 3 is just 3. So now I've got plus root e to the 5th over 3, which is the same thing as what I have over here. So they really are the same. So the last bit, which you may have noticed, is here I've got a plus or minus. Here I've just got a plus. let's do that thing again where we check to make sure all our answers would work in the original equation. So if I have negative 2 minus the root, which is a positive number, that means my overall x value is going to be negative. And so if I have a negative number that is more negative than negative 2, which it clearly is here, then if I plug that back in here for x, let's imagine taking this and plugging it in for x, I'd have negative 2 plus 2, make 0 together. But then I'd have a negative value here, so then I'd be taking natural log of a negative, and that's outside the domain of log. So it's not really plus or minus, it really is just the plus. Okay, let's do the next one. Okay, so this one, we really do have to use log simplification properties to solve. Well, I guess we don't. I guess we could add the log on this side, and then we could exponentiate, and then we'd be using exponential properties instead of logarithmic properties. I guess we could do that. Let's do it two ways again. So on the left, we remember that a log minus a log is the same thing as a log of the inside divided by the other inside, like this. So now I can raise both sides as the exponent of a base of 2. And so now I've got x over x minus 2 equals 2 to the 4th, which is 16. Let's multiply. So 16 times x minus 2. So that's 16x minus 32. And so now let's add 32, and let's subtract x. So that means x is 32 over 15. Great. Okay, let's do it the other way. So here I've got log base 2 of x equals 4 plus log base 2 of x minus 2. Now let's do the exponentiation. So here I've got x equals 2 to the 4th plus log base 2 of x minus 2. I need to isolate the x's, so we'll need to simplify this. So this is the same thing as 2 to the 4th times 2 to the log base 2 of x minus 2. So now that's 2 to the 4th is 16. 2 to the log base 2 of x minus 2 is just x minus 2. And so now it's the same as here, and so it's going to end up being the same. Problem 5, e to the 2x minus 2e times e to the x equals negative e squared. Lovely. Okay. So I have a couple of thoughts here. Let's try something on this side. Let's try and bring these together. So here I've got e to the 2x minus, this is 2 times e to the 1st times e to the x. So that's e to the x plus 1, negative e squared. It's not totally clear what I should do here. I mean, I guess I've got a lot of e's, so I could take the natural log of both sides and see where that gets me. So here I'm subtracting on, well, here we got to think for a minute. So here you might be tempted to misremember the logarithmic simplification. You might say, oh, subtraction turns into division. So you might wrongly say, this is like saying natural log e to the 2x over natural log 2e to the x plus 1, and then simplify from there. But that's not the direction the simplification goes. The simplification rule would look something like this. Natural log of a over b, so division on the inside produces natural log a minus natural log b on the outside. But that's not what we have up here. So it seems like this approach is, I'm not feeling terribly optimistic about. So let's do this instead. What I'm recognizing, so this is a bit of a trick. E to the 2x is the same thing as e to the x squared. And then this is e to the x, negative e squared. So notice that I've got an e to the x here and an e to the x here. So let's define a new variable p as e to the x. So now I've got p squared minus 2e times p plus e squared equals 0. Move the e squared over. Okay, so this is just a quadratic. It's, something squared minus something plus something. So let's try and factor it. Or you can complete the square if you want. So pp, so this is e squared, so it makes the most sense that I should have e on the outside here, because then I know I'll have e times e gives me e squared. Is this going to work? So p squared minus ep minus another ep is minus 2 eps, nice, plus e squared, okay. So really it's just p minus e quantity squared is 0, which just means that p equals e. But remember, I'm not actually trying to solve for p, I'm really trying to solve this one over here. So e to the x equals e, meaning x equals 1. Okay, let's just make sure that makes sense by going back to the original. What if I plugged in x equals 1 here? I'd have e to the second power minus 2e times e to the first power equals negative e squared. So e squared minus 2e squared equals negative 1e squared. That works. Great. So from sort of an A-level problem perspective, just be on the lookout for when you have quadratic equations, but quadratics not in terms of x, but in terms of some other expression involving x. Okay, hope this was helpful.